Hello students, this is Mr. Martin, and today we're going to talk about Chapter 11, the Dynamic Planet. Now, geologic time is an extremely long period of time. In this chart, you see that talk about geologic time in millions of years. For example, in 0.01 millions of years ago were the first humans. So relatively speaking, humans have been on this planet a very short amount of time. And as time continues to decrease or go back in time, you see different eras in geologic time. For example, the Jurassic period, we all know, is the part where the dinosaurs lived about 145 to 201 million years ago. As you keep going back, you see more and more different periods of geologic time. And the Earth is actually dated back to approximately 4,600 millions of years ago. So we know from geology that there's relative time and superposition. The principle of superposition is that the youngest bed of rock is at the top of a formation and it's oldest at the base. So unless it's been disturbed, toppled over, moved, or bulldozed, your top layer is your youngest layer of rock. So we know about the Earth by looking at rocks, and you can see places like the Grand Canyon, where the rock layers are older and older the closest you get to the bottom of the Grand Canyon. Now, trying to figure out the age of rocks is done by radiometric dating. And the oldest rocks that have been found on the planet are approximately 4.4 billion years old. We've also tried to figure out what in the world is in the center of the Earth. Scientists have drilled down 12.2 kilometers or 7.6 miles, and that's as far as we can actually physically go at the present time. So the knowledge of what's inside the Earth is from indirect evidence. Seismic waves from earthquakes pass through different layers differently, and they speed up in cold, rigid regions and slow down in hotter, more plastic or fluid regions. And so we figured out that the core is the hottest and the surface is the coolest. And as we look at these seismic waves, when there's an earthquake, they travel through the Earth and arrive at different points in the planet at different times. So when you look at the difference in the different points in the different times, scientists can figure out what are the properties of the inside of the Earth. So we know that the core is at the center, the mantle is in the middle, and the crust is at the surface. The core makes up 1/3 of the Earth's mass, 1/6 of the volume, so it's very dense. It's solid iron in the inner core at 10,800 degrees Fahrenheit. The outer core is molten liquid iron. The mantle makes up 80% of Earth's volume, and the lower mantle is hot enough for rocks to flow very slowly. The crust is the outer layer, which is where we live. There's 8 elements that make up 98% of the crust by weight. Almost half of our crust is in oxygen, not air oxygen, but oxygen blended with other things that make solid matter. And our continental crust is lower in density than the oceanic crust. Continental crust is made of silica and aluminum, and oceanic crust is made of silica and magnesium. The lithosphere is the rocky layer made up of the crust and the uppermost mantle. The asthenosphere is a plastic layer below the crust. Convection currents in the asthenosphere is what drives plate tectonics. Now, rocks in the asthenosphere are plastic, meaning they can flow in response to deformation. Even though it can flow, the asthenosphere is still made of solid, not liquid rock. You can think of it as kind of a silly putty. Just realize that when they talk about the plastic mantle or the plastic asthenosphere, it's not actually plastic as we know it. It's a plastic-like substance. So Earth's structure, if you took out part of the Earth and looked at it, the inner core is the very middle, and then you have an outer core, which is liquid. Remember, this is solid, this is liquid. And then you have a lower mantle and an upper mantle. And at the edge of the upper mantle, you've got the plastic mantle, which is that asthenosphere, a rigid mantle, which is rock, and then a continental crust, which is the part that we live on. Now, the distance from the core to the crust, this is an interesting map. If you look at the center of the core and started in Anchorage, Alaska along the surface, it's approximately from Anchorage, Alaska to Fort Lauderdale, Florida. So that's pretty much across the entire North American continent is the distance from the surface to the center of the Earth. Now, elements that are found in the Earth's crust are oxygen, which is 46.6%, silicon, which is 27.7%, 8.1% aluminum, 5% iron. Then you have some calcium, some sodium, some potassium, some magnesium, and all other elements are only 1.5% of the Earth's crust. Now, Earth has a magnetic field which is generated by the fluid outer core. This core flows and is moving actually at 60 kilometers a year, so it actually flows relatively fast. Magnetic poles are not the same as the geographic poles. The Earth's magnetic field reverses from time to time, called magnetic reversals, and there's been 4 reversals in the last 9 million years, so time to time is not very often. And this provides important evidence of plate tectonics. So Earth's magnetic field is caused by this flowing mantle, and it is not exactly true north. True north is the very point where the Earth rotates on its axis, and true south is the very point where the Earth rotates on its axis. But the North Magnetic Pole is actually not exactly where the true North Pole is. It goes through the Earth at this angle, where the rotation of the Earth rotates at this angle. So when we talk about Earth's materials in the rock cycle, a mineral is the inorganic or non-living natural compound having a specific chemical formula and possessing a crystalline structure. So your minerals are very pure. A rock is an assemblage of many minerals bound together, or a mass of a single mineral, or undifferentiated material, or even solid organic materials such as coal. So a rock has lots of different things in it, where a mineral is a pure natural compound or element. There's 3 basic rock types: igneous, which means it was molten; sedimentary, which means it formed from layers of sediment; and metamorphic, which means that the igneous and sedimentary rocks have been subject to heat and pressure, changing them into a different form. Now, igneous rock is rock that cools and solidifies from magma. Magma at the surface is called lava. An intrusive igneous rock cools below the surface, meaning it cools slowly. So you end up with rock that has smaller or no crystals. Extrusive igneous rock cools on the surface. And so that's where you have the volcanoes, and it cools very quickly. For example, you have here pictures of intrusive granite, and granite is igneous rock that is cooled below the surface. And you have extrusive basalt, which is igneous rock that came to the surface in molten form. Sedimentary rock is different. Weathering disintegrates and dissolves these rocks into grains and fragments called clasts. And erosion by gravity, wind, water, and ice carries these clasts. And sedimentary rocks are classified into clastic and chemical. So sedimentary rocks that we see are often in the forms of sandstone and limestone that you can see in various parts of the country. It has a very different look, sedimentary rocks. You'll have these striations of different layers of sediment. Now, metamorphic rock is different. It is igneous or sedimentary rock that is transformed through high pressure or heating. Contact metamorphism occurs in the upper crust when rising magma cooks adjacent rock. Regional metamorphism occurs deep in the lithosphere. So the metamorphic processes is this heat from magma that is in the magma chambers heats the surrounding rock or heats the rock in here, and it will actually change the properties of the existing sedimentary and igneous rocks. So there's a rock cycle on the Earth, and this rock cycle is over millions of years. But you have flowing magma that cools and solidifies into igneous rock that weathers and erodes into sediment that is compacted over time on the surface into sedimentary rock, which is heated again and transformed into metamorphic rock, which then can be melted again into magma. So the movement of the Earth actually creates a rock cycle. And you see these cross layers. You can have sedimentary rock that can weather down and end up back in sediment, or it can be melted. So scientists started to look at this geologic time and movement and came up with the theory of plate tectonics. And this is the idea that the continents actually drift. Alfred Wegener proposed this in 1912 based on geologic evidence. The theory now is called plate tectonics. And we see this in a lot of areas. One area that we look at is seafloor spreading. So our continents do move. And it's hard to think about our continents moving, but 225 million years ago, there was a supercontinent that they named Pangaea. And it's where all the landmass was on one side of the globe. And over 225 million years, this has changed because of the continents moving on these continental plates. So about 65 million years ago, we still had a pretty compact world. But as the seafloor spreads, this is what our world looks like. Most of our land mass is still on this side, and the Pacific Ocean is still on the other side, that is the largest ocean and the area that the continents are moving towards. So when you look at the seafloor, you can actually look in the middle of the ocean where this mid-ocean ridge is, which is the seafloor area where magma comes up in these fissures here. So the magma comes up, creates new rock. The further that the seafloor spreads, the older the rock. So scientists take rock samples in the Atlantic Ocean, for example. The closer to Europe or the closer to America you get, the older the rock. The closer to the center of the ocean, the younger the rock. So if we look at this is the Mid-Atlantic Ridge. As I say, as you go closer to land this direction and you sample the rocks at the bottom of the ocean, you see that this becomes older and older and older, suggesting that this part of the globe is moving in an easterly direction. Same thing here. If you take from the Mid-Atlantic Ridge towards North America, you get more older and older rocks, suggesting that this part of the world is moving towards the west. You have older ridges around the world where the same phenomenon is occurring, where the oceans are moving in two directions. So as these plates move from a spreading center, they collide into other plates. For example, if this plate is moving this direction, it's going to collide into another plate. And this continental plate holds its position, and the oceanic plate slowly goes underneath it. So the Earth's major plates, you have the huge Pacific plate, you have the Caribbean plate, North American plate, the Eurasian plate, and all of these plates are moving in different directions. For example, if this is the mid-ocean ridge, this plate is moving this direction in a primarily eastern direction, and these plates are moving in a primarily western direction. This is where the seafloor spreads. Then these plates are moving in this direction, so you're going to have a different subduction area here than you would over here. Now, as we look at transform faults and fracture zones, along these plates you have long ridges of where the plate boundary is, and in places where there's been a shift, and that is where the transform fault is, and it's fractured. So you have some Earth moving faster in different places along these fault zones. They're not exactly direct lines. We also know about the plate boundaries from earthquakes and volcanoes. If you take a map and you put the plate boundaries on there, like the Mid-Atlantic Ridge, the Caribbean plate, the Pacific plate, at the boundaries of all these plates are the places where the Earth is moving. So subsequently, it's the places where the volcanoes and earthquakes are always located at. In the center of a plate, you're not going to have volcanoes or earthquakes because you have that crust that acts as a top over the mantle. But the fissures where they come through are located along the edges of the continental plate boundaries.